guys, this is Algebra 1, topic 5. We're going to learn about piecewise functions. In this topic, we'll think about how we can use piecewise defined functions to model situations and solve problems. So in this lesson, we have 4 lessons only, but piecewise functions could be a little bit tricky. So you need to follow through well. Topic vocabularies are absolute value function, axis of symmetry, ceiling function, floor function, piecewise defined function, step function, and vertex. So let's get started. Here's the topic 3 project. Okay, lesson 1. The absolute value function. In this lesson, you will analyze functions that include absolute value expressions. So we'll talk about absolute value function, axis of symmetry, and vertex. First, let's look at exploring reasoning. Group of students are hiking from mile markers 2, 6, and 8 to meet at the waterfall located at mile marker 5. Do you know what mile markers are? Have you ever been hiking? Yes, if you go on a hiking, you have a hiking trail and you might have seen those stones or a wooden frame where they tell you how many kilometers or how many miles. So those are the markers. They let you know the distance you traveled if you have started from the beginning, 0 mile mark. Okay, so this is mile 2, mile 5, mile 6, 8. So you can see that direction goes from left to right. So you start from 0, and that's 2 miles, 5 miles traveled, 6 miles traveled, 8 miles traveled, and so on. Okay, that's how it works. So the picture shows out the waterfall at mile 5, and there are 3 groups of students, one at mile 2, one at mile 6, and one at mile 8. Okay. How can you use a mile marker to determine the number of miles each group of students needs to hike to the waterfall? So the group of students who's located at mile 2, they just need to go 1, 2, 3 miles more to get to the waterfall. What about group that's at mile 6? They need to come back. So they need to go backwards, right? So subtract 1, go backwards 1 mile. What about mile 8? 8 minus 3 is mile 5. So they need to come back 3 miles. Okay. So yeah, they have different distances away from the waterfall. Part B, make a graph that relates the position of each group on the trail to their distance from the waterfall. Okay, first, let's record part A. Okay, I'm gonna say you subtract the number of each mile marker from 5. Okay, so 6 minus 5, wait, from 5. So 5 minus 6 is -1. 5 minus 8 is -3. 5 minus 2 is +3. And then how far away is talking about the distance. Distance cannot be a -1. Only when we're talking about speed and, we can say, oh, it's going backwards, right? Or time going backwards. So in distance, you always have positive numbers for distance. So in this case, we're going to find the absolute values of the differences. So +3 is already +3, but still the absolute value of +3 is 3. Absolute value means you just make everything positive, right? So absolute value of -3 would be 3, and so on. Okay. Part B, make a graph that relates the position of each group of the on the trail to their distance from the waterfall. And how would the points in your graph in part B change as the groups of students? Oh, that's actually part C. Okay. So you're gonna put the points 2, 3 because relates the position of each group. So we're gonna say number X is the number of miles. Okay, is their position. Okay, then Y is gonna represent the distance from the waterfall. Okay, whoops. So that means we have a point 2, 3. Position is mile 2. And then mile 2 is 3 miles away from mile 5, the waterfall. Then we have another point 5, which is the waterfall is 0 distance away. And then we have 6, how many distance? 1 mile away. 8, 3 miles away. Okay, so in the graph, you need to have mile marker and then distance. Okay, and 1, 2, 2, wait, 3, and then 1, 2, 3, 4, 5, 0, and then 6, 1, and then 7, 8, 3. Okay, so these are the points you should have in the graph of part B. How would the points in your graph from part B change as the groups of students approach the waterfall? So if they start moving closer and closer to the waterfall, how would the points change? Because Y is the distance from the waterfall, they're gonna go closer and closer to 0, right? Distance is gonna get lower. So all the points, except for the 5, 0, all the points get closer to 5, 0 from each side. Because if they move here, they're gonna be in mile 3. And this is gonna represent 3, how many distance away? 2 miles. So 3, 2. And then 4, 1, they're gonna get closer and closer to 5, 0. Okay, so if they go closer and closer, they're gonna get closer and closer to 5, 0. Okay, not just any 0, 5, 0, because the waterfall is at mile 5. Okay, does that make sense? Okay, so in this lesson, we'll think about what the key features of the graph of the absolute value function are. Example 1, graph the absolute value function. What are the features of the graph of f of x equals absolute value x? We're going to look at the function of absolute value. This is called the parent function. It means there's no transformation in the graph. This is the pure and original graph of absolute value function. Okay. Let's use Desmos and see what it looks like. So f of x is equal to absolute value x. Okay, so in Desmos, that bar, absolute value bar, could be written as ABS parentheses. Okay, so whatever goes inside the absolute value bar would go inside the parentheses after absolute value, ABS sign. Okay, and that is what the absolute value function looks like. You start from 0, 0, and you have 1, 1, 2, 2, 3, 3, negative 1, 1, negative 2, 2. They basically tell you how much they're away, how much distance they're away from 0, 0. Okay, so the points here. We'll have a vertex, 0, 0. That's called the vertex, the lowest point, or where it starts from. Okay, that's your standard point. It's the turning point of the graph. And then if you go the positive side to the right, 1, 1, x is equal to 1 is 1 distance away from 0. 2 is 2 distances away from 0, 2 units away, right? Then -1 is 1 units away from 0, -2 is 2 units away from 0, and so on. That is the absolute value function graph. And there's another vocabulary word, axis of symmetry. Axis of symmetry is the line x is equal to 0. Axis of symmetry has the vertex. And when you fold the graph in half using the axis of symmetry, your graph must lie exactly onto itself. Okay? So vertex is going to be your point. Vertex is a point. Okay? It doesn't have to be 0, 0. It could be any point, but that's the turning point of your graph. Axis of symmetry is a line. Okay? So by definition, axis of symmetry intersects the vertex and divides the graph into 2 sections. Okay, it intersects the vertex and divides the graph into 2 sections or pieces that are images of each other under reflection. Okay, so what are the domain and range of absolute value function? We learned about domain and range in the last topic. So what are they? Okay. So domain would be all the possible values for x. Range would be all the possible values for y. So what is a domain? Do you see all the x numbers? Your graph is extending this way, right? Can x be any number, or is there any number that x cannot be? Well, do you have fraction like 0.5? Yeah, 0.5 decimals and fractions are here. You have a point here, 0.5, 0.5, right? 1/2, 1/2. It does include all negatives and all positives. So yes, it includes all real numbers. So you're gonna say all real numbers for domain. What about the range? Look at all the y values. What do you see? Look at the table as well. All the y values are positive, right? The graph does not go down. There's no graph here. So your y values cannot be negative in this graph. So the range is y. All the y values are greater than or equal to 0. Okay? Okay. Let's look at the next page. Example 2. Transform the absolute value function. All right, now the transformation. Are you ready? How do the domain and range of g of x equals 2 times absolute value x compare with the domain and range of f of x equals absolute value of x? First, let's compare the graphs of g and f. We've done transformations, right? How does the graph change from f to g? Right, the black one to the red one. Okay, does it go up, down, left, or right? Does it move? Does it have a translation? Or does it have a reflection? Okay, let's not talk about reflection since we didn't do that. Does it have a stretch? Do we have a vertical stretch? Do we have a horizontal stretch? Do we have a compression? Right? So look at horizontal. It's obviously your vertex stays the same, so it obviously does not move. It does not translate, right? But rather it is a stretch or compression. So horizontally, your points are moving towards the y-axis. So this is a horizontal compression, which means vertically, what is it? Your points are moving upwards, right? So vertically, it's a vertical stretch because it's moving away from the x-axis. It's a vertical stretch, right? All right, so looking at the domain and range, we still have all values, all real numbers for a domain. X could be any number. But y could still only be positive numbers even though they grow a lot faster. They go bigger a lot faster, right? So they're still non-negative outputs. And so domain and range would be the same. That's okay. Okay, so domain and range of the function g are the same as those of function f would be your answer for this question. What about the next one? How do the domain and range of h of x equals -1 times absolute value x compare with the domain and range of f of x equals absolute value x? So this is the original parent function, absolute value x. Look at -1 times absolute value x, which is basically negative absolute value x. This is how it looks like. Because why? Make a table. 0 is going to be 0, 0. But what about 1? 1 absolute value and then a negative is -1, right? Because 1 absolute value -1 is -1. Because absolute value 1, you need to do that first. What about -1? -1 still is -1, right? So then everything is flipped. So it's a reflection on the x-axis. How do the domain and the range change? Domain would still be all real numbers. X could be any number, right? You can plug in any numbers. But the y's, the range would change from all positive to all negative numbers, including 0. So y is less than or equal to 0. So compare and contrast your domain. Domain are all real numbers, but the range of h would be y is less than 0. Okay. So domain is the same. Range is the opposite of the range of f. All right, so you need to be able to compare the functions using transformation. So look at try number 2. How do the domain and range of each function compare with the domain and range of f of x is equal to absolute value x? So you're going to compare both of them from f of x equals absolute value x. So how does this change? Okay. See if you can describe it by yourself. Come back when you're ready for answers. All right, you already know that f of x equals f of value x would look like this. Okay. You can use decimals to check your answers, but please don't make a habit to use it every time you're solving a problem like this because you won't know how to graph if you keep using decimals before you even learn how and get comfortable with using graphing. Okay, so how do you graph absolute value x divided by half? You plug in some numbers, put in 0, so make a table of value. If x is 0, y is 1/2 times absolute value 0, which is 1/2 times 0, which is 0. Okay, so 0, 0. What about positive 1? 1/2 times absolute value 1 is 1 divided by 2. So that's 1/2. 2. 1 over 2 times the absolute value 2. So 2, positive 2 divided by 2 is positive 1, and so on. What about negatives? Okay, 1 over 2 times the absolute value negative 1 is positive 1 divided by 2. So it's positive 1 over 2. Negative 2, 1 over 2 times negative 2 absolute value, negative 2 would be positive 2 divided by 2, which is positive 1. So all your range would be positive. So you just need to compare domain and range. What happens to the domain? They stay the same. So check your answers. G of x would be half absolute value x. Okay, so that's the blue one. See, your domain doesn't change. It's all real numbers. What about the range? Is it still all positive numbers? Yes, the vertex doesn't move. So domain and range stay the same. Okay, domain and range of G are the same as F, would be more accurate. Okay, part B. What about h of x is equal to negative 2 times absolute value x? Make a table and see how the numbers change. 0, comma negative 2 times absolute value 0 is 0. Okay, 1. Negative 2 times absolute value 1 is a negative 2 because absolute value 1 is positive 1, but positive 1 times negative 2 is a negative 2. Does that make sense? You need to do the absolute value first and then multiply that number to the negative 2. So 2 would be negative 2 times absolute value 2, but that's negative 4. What about the negative numbers? Negative 1. If you put negative 1 in there, then negative 1 becomes a positive number, but you still have to multiply that with a negative 2. So it's a negative 2. Negative 2, if you put negative 2 as a value in there, you're going to get negative 2 times positive 2, which is negative 4. Okay, so your domain could still remain the same, but your range is going to be all negative numbers, including 0. So let's check your equation H. H of x is equal to negative 2 times absolute value x. You see that? So let's get rid of the blue. And there is a horizontal compression and vertical stretch as well, but it's also gonna be reflected across x-axis. You see that? So all the values of domain, all the x values are still the same. They're all positive, all negative, and 0 numbers. But range used to be all positive numbers. Now it's all negative numbers. So here, what can we say? The domain of H is the same as F, but the range of H is the opposite of F. It's all negative numbers. Okay. So we learned how to compare domain and range for the absolute values so far. Why don't we stop here, pause here, and we'll continue with the next examples in the next video. Okay, see you later.